Hey YouTube, it's Dimitri, and today we're going to talk about model errors. So we're just going to talk about general theory, a few different types of ways to measure the model errors. And I know this isn't necessarily specific to time series. This is just a general statistic concept, but we're going to need this to build deeper into our analysis of analyzing time series, model fitting, and kind of just the constructs of how we're going to move forward. So let's just dive on in. All right, so we're going to start off with MAPE, which is the mean absolute percentage error. To calculate this out, MAPE is going to be equal to, mathematically speaking, 1 over n times the summation of, say, I is equal to 1 to n. And then this is going to be the absolute value of y of I minus y hat of I, which is going to be your prediction, divided by the absolute value of y of I. And then this whole thing is going to be multiplied by 100 to give you percentage. If you're not mathematically inclined, simply this is just saying this is going to be the average of the absolute value, which is your actual values, minus your predicted values, divided by the absolute value of your actuals. Okay, so why is this useful? A lot of people really like this measure because it is a percentage error. So it gives you kind of a non-scale dependent error, which is meaning that like 2% error is 2% error. It doesn't matter which data you're putting in. You can easily compare different types of models because you can look at the percentage error, which is all going to be in the same scale. The downside to this, which mathematically, if you've noticed here, the denominator is going to be y of I. If you have any model where this could be 0, dividing by 0 is undefined. So there's no way to actually calculate the error if your actual values has a 0 in it somewhere. So this is really, really risky for a lot of different types of models. If you're doing time series, for example, and you do any differencing or you have data that bounces around the 0 line at all, that's a deal breaker. You can't use this. It's going to be undefined. It's not going to be an accurate measure of your model error. Theoretically speaking, all stochastic processes, so time series, have to start at 0. It's a defining characteristic of time series. Everything starts at 0 and then goes up. In practice, this doesn't really matter because we never model time series from the beginning of time. So if you model any stock prices, for example, it'll start at some level value. But this isn't the best type of measure for error, especially for time series. It's great for other things, but not really the best in this scenario. And something else I wanted to kind of mention here is that the model errors are not the same on positive and negative. So if you're over predicting versus under predicting, your MAPE is sensitive to this. So just to give you a quick example what this means, MAPE has a heavier penalty on positive errors. So if you're over predicting, it penalizes your model more, whereas you're under predicting, it doesn't quite penalize as heavily. Some of you are thinking, why does this matter? Different types of models, different types of scenarios. So for in financial data, right, let's say you're predicting profits, right? You don't want to be over predicting profits. It's not conservative. You'd rather under predict profits and then in the real world do much better and be excited and have your stock price soar than you would having, all these over predictions. And then when reality comes out, your model does terrible, your stock price doesn't do well, profits are down. Anyways, it's just not a good scenario for this example. Much of time series, you don't want to be either under or over predicting, but I don't like the bias of this model. If you look at this Excel here though, I'll give you a quick example. You can see the Y column and the P column. So Y is going to be your actuals, P is going to be your prediction, and then I have this MAPE column here. If you look at the equation, all it is the absolute value of the actual minus the predicted divided by the absolute value of the actuals. And then to do all the fancy stuff, right, we just take the average of all of these MAPEs, which is how you would calculate this. And you can see here, it's 0.29. If you switch the Y and the P column, so in this case, I'm just switching them. So the distance between your actuals and your prediction, so that error is going to be the exact same for every observation. But as you see when you flip them, so now that we're over predicting and do the same calculation here, the error is 0.4479. That's huge, right? Going from 0.29 to 0.44, almost 0.45, that's a huge change. So in this case, I'm not the biggest fan. And just to kind of point out here too, I mentioned it down here, you can look at this paper by Makridakis, I think that's how you pronounce it, from 1993. It's a whole paper on MAPE and basically some of the issues with it. But in general, MAPE's not going to be the best measure for doing time series. All right, so next we're going to look at the MAE, which is the mean absolute error. This is a very intuitive kind of error concept to think about. This is just going to be the average of your error terms. One thing to think about and why a lot of these take like the absolute value or they take the squared value. So MSE, mean squared error, is another one. The reason you do this is because if your errors were slightly positive and slightly negative, and then if you add all those negatives and positives together and they cancel out, your model will show a 0, meaning it has 0 error in the model. We all know that's not accurate, so we have to either take the absolute value or we have to square the error term. All right, so the mean absolute error is exactly what we're thinking it is, which is going to be MAE, mean absolute error. This is just going to be the average, so 1 over n times the summation of I equals 1 to n, and then the absolute value of y of I minus y hat of I. So speaking simply in non-math terms, it's just going to be the average absolute value of your actuals minus your predictions. So in this case, the MAE can be a good measure, right? It just takes the absolute error of the model. It's an okay measure. It's robust to large outliers, which is something that's very important. But one of the things to point out with the MAE is it is scale dependent. So scale dependent means that depending on the data you have, the number that comes out of the MAE is going to be dependent on the scale of your Y variables. So if your Y variables are in the thousands, you're going to have a very large MAE. If your Y variable was in, say, the 0 to 1 range, so it's like a percentage, your MAE is going to be very small. What this means is you cannot compare MAEs across different types of data. So if you're using the same data for model development, you can compare MAEs for different models, but you cannot compare MAEs across basically different data sets or data structures. You should be careful as well if you're using a development data sample and an out-of-time data sample or a validation data sample. You should be careful to look at the data and make sure the scales are relevant and that that's not skewing some of your error measure. So this is a downfall and something I think a lot of people don't look at. When data changes with MAE, you have to be careful in what you're comparing. And I should note that the MAE basically is robust to the outliers, which I did mention, but it doesn't have a lot of skewedness to it. So it's a good measure to use. But we're going to look at something that's very similar to this. And this is going to be mean squared error, which I mentioned before. And the mean squared error is going to be 1 over n times the summation of I equals 1 to n times your actuals minus your predicted values squared. So this is the, again in simple terms, right, this is the mean or the average squared error. So this is going to be your error here, squared. This is also another good measure to use, but the thing with this is that the mean squared error doesn't have a lot of meaning in the sense that it's your error and it's squared, but it's hard to conceptualize what that squaring is. I'm not a big fan of it as well because when you square things, if it is less than 1, so if your errors are small between 0 and 1, you will end up with an even smaller error as you square them. This is just a mathematical kind of property. But the issue is that this doesn't provide a lot of meaning or intuition, at least in my opinion, which leads us to kind of the final type of model error we're going to be looking at here. And this is just the root mean squared error. This is just going to be the same thing as the square root of the MSE, so mean squared error, which is going to be the square root of 1 over n summation of I equals 1 to n. And then this is going to be y of I minus, so your actuals minus your prediction squared. Why is this important? Why does this add value? Why do I like this measure? The reason being is that while the mean squared error, which is also scale dependent, has, I don't know, some value to it, it doesn't really tell us anything in a kind of measuring realm, I guess is the way to say this. The root mean squared error actually is going to be equal to the distance. So the distance between your actuals and your predicted is going to be the root mean squared error. The reason I like this is that the squared part here makes everything positive, so you can use this as an actual measure of error. The squared root piece here, so this whole squared root piece, will cancel out with your squared part, and you're just left with the distance. So when your errors are evenly distributed, your MAE and your RMSE are going to be the same. I think that's important to note. The variance in your errors as they change will actually make the root mean squared error different from the MAE. The root mean squared error also penalizes larger errors than MAE due to the squaring before the averaging. So I think that's important to note as well. The root mean squared error will actually penalize data points that are further off. So if it's an outlier, it is not robust to it. It'll give it a larger penalty than it would if the value was much closer. This has pros and cons, right? You have to think about this again conceptually. Not every scenario is going to want to favor large errors. And time series, I think from a conceptual standpoint, I really do favor the root mean squared error for this feature. Time series is difficult, and a lot of times, which we have not covered yet, but a lot of times when you get into dynamic models, once you have one really large error, the model will essentially use that error to predict forward in time. It perpetuates the error forward. So if you have large errors, even just one or two outliers, it might destroy the integrity of the model. It'll destroy essentially your forecast, your reliability of the model. And it's one of the large complaints people have in time series, especially when we start diving in deeper to the dynamics of models, not the static structure that we've been looking at. But I favor the root mean squared error for this reason. We're going to be doing in the next video, we're going to look at our linear model and our multiplicative model, and we're going to look at different errors. We're going to compare them and we're going to discuss them. But for this video, I just wanted you guys to understand there are all kinds of ways to measure errors. There's not a correct way to do it or a wrong way to do it, but you need to understand the math behind this, and you need to understand the pros and the cons. As I mentioned here, right, the MAE, the root mean squared error, and the mean squared error, they're all scale dependent. You cannot use these across different sets of data, so it is very dangerous to use these on different models that are different types. If you're using this on development versus validation, development versus out of time, if your data is changing, that change in data, that change in sample is going to have drastic effects on your model error. Time series is notorious for having small data sets, so it is not appropriate a lot of times to be comparing these errors into different samples. So for our purposes and what we're doing multiple models on the exact same data set. It is completely appropriate to be using the scale-dependent measure of errors. Like I mentioned, the MAPE, the mean absolute percentage error, is awesome because it is not scale-dependent. It is put into a percentage format. It has a lot of advantages, but it does have the big downfall that it is undefined when divided by 0. This is going to kind of throw a wrench in our problem as we're moving forward. So we're not going to use the MAPE, but we are going to be using the root mean squared error, and we might even look back at the MAPE as in our examples, I don't believe we have any 0 values. So anyways, that's just the basics of looking at the model errors here. I want you guys to take away from this video that statistics is very unique and dynamic, and looking at all these different aspects is important. I think a lot of people just pick up one thing, they pick up like a test and they look at the final number, and then they just compare numbers. And I'm going to yell at people and throughout these videos and show you the pitfalls of new statisticians. Don't rely on the numbers. You need to look at the mathematical theory. So when we look at, for example, right, the MAE versus the RMSE, what are the pitfalls? Why would you use one over the other one? Does it make sense to even use the measure that you're using? From a validation perspective, so somebody who works in model validation and model development in the past, these are the crucial steps that are going to determine if your model was done correctly or if there are better opportunities out there of different types of models. But just take this from the standpoint of understanding the mathematics is crucial in statistics. Understanding the theory, being able to apply those theories to your problem and understanding them better is going to make you a better statistician and a better quant. Anyways, thanks for watching. Don't forget to like, share, and subscribe. And as always, until next time.